right now, so I just wanted to shout out, this is Philipp Oppermann's blog, and what we're going to be working on today, or working our way through today, is the Introduction to Paging section. So let's get that set up. Actually, let's go over here really quickly. Documents, dev, BlogOS, and I think we're up to date on this. Git status, we are. And then actually, let me make this a little smaller, shorter, so that I can make the font bigger. There. Cargo run. If we run it, we'll get our operating system running. Guess I had to rebuild. Did I crash? Oh, that's right. The last thing we got working was the keyboard. So I can type keys on the keyboard now. And it handles the keyboard interrupts correctly. And then this dot is just printed out using the built-in timer, the hardware timer that QEMU is emulating. All right, pop out my chat, get squared away, and then start recording for YouTube. Yes, quit that. Okay. Oh, it's not dying. That's not good. I can control C it though. Okay. I'm not sure why I couldn't close the window. I had been able to in the past. All right. But let's do this. Philipp Oppermann's blog, Introduction to Paging. This post introduces paging, a very common memory management scheme that we will also use for our operating system. It explains why memory isolation is needed, how segmentation works, what virtual memory is, and how paging solves memory fragmentation issues. It also explores the layout of multi-level page tables on the x86-64 architecture. Memory protection. One main task of an operating system is to isolate programs from each other. Your web browser shouldn't be able to interfere with your text editor, for example. To achieve this goal, operating systems utilize hardware functionality to ensure that memory areas of one process are not accessible by other processes. There are different approaches depending on the hardware in the OS implementation. And as an example, some ARM Cortex-M processors used for embedded systems have a memory protection unit, MPU, which allows you to define a small number of memory regions with different access permissions. On each memory access, the MPU ensures that the address is in a region with the correct address permissions and throws an exception otherwise. By changing the regions and access permissions on each process switch, the operating system can ensure can ensure that each process only accesses its own memory and thus isolate processes from each other. On x86, the hardware supports two different approaches to memory protection, segmentation and paging. Segmentation was already introduced in 1978, originally to increase the amount of addressable memory. The situation back then was that CPUs only used 16-bit addresses, which limited the amount of addressable memory to 64 kilobytes. To make more than these 64 kilobytes accessible, additional segment registers were introduced, each containing an offset address. The CPU automatically added this offset on each memory access so that up to 1 megabyte of memory were accessible. The segment register is chosen automatically by the CPU depending on the kind of memory access. For fetching instructions, the code segment CS is used, and for stack operations, push-pop, the stack segment, SS, is used. Other instructions use the data segment or the extra segment. Later, two additional segment registers, FS and GS, were added, which can be used freely. In the first version of segmentation, the segment registers directly contain the offset, and no access control was performed. This was changed later with the introduction of protected mode. When the CPU runs in this mode, the segment descriptors contain an index into a local or global descriptor table, which contains, in addition to an offset address, the segment size and access permissions. By loading separate global local descriptor tables for each process that can find memory accesses to the process's own memory areas, the OS can isolate processes from each other. By modifying the memory address before the actual access, segmentation already employed a technique that is now used almost everywhere, virtual memory. I don't think virtual memory was invented before. I mean, I should say, I think virtual memory existed before this whole segmentation idea came to be. It was used in mainframes, I believe. I don't know. I should look that up. Virtual memory. The idea behind virtual memory is to abstract away the memory addresses from the underlying physical storage device. Instead of directly accessing the storage device, a translation step is performed first. For segmentation, the translation step is to add the offset address of the active segment. Imagine a program accessing memory address hex 1234000 in a segment with offset hex 1111000. The address that is really accessed is hex 2345000. I thought the segment selector was offset by 16 bytes. I guess I'm wrong, or I guess I remembered incorrectly. I just need to look it up because I want to understand. Yeah, it is. It's offset by 16 bits. Sorry. So you don't add it. Oops. Where were we? We were over here. So I don't think it's this way, right? I think if you add this to this, if the segment has the segment register has 1111000, it'll actually be x2345000 plus 111000 plus another 0, right? That's what I'm seeing here, that the segment actually was 16 bits off. Sorry, 4 bits off. 4 bits off. So shifted up by 1 hex digit. So it would be added to 0000. Oh, sorry. This is if we start at 1234, right? It'll be 2344000. That'll be the actual address. I think this might be just okay. It's at the detail. I'm getting in the weeds. But that's the idea, is that the segment address actually extended the memory address by another 4 bits, and that's how you got up to the a 20-bit or 1 megabyte address space. All right, sidetracked. To differentiate the two address types, addresses before the translation are called virtual, and addresses after the translation are called physical. One important difference between these two kinds of addresses is that physical addresses are unique and always refer to the same distinct memory location. Virtual addresses, on the other hand, depend on the translation function. It's entirely possible that two different virtual addresses refer to the same physical address. Also, identical virtual addresses can refer to different physical addresses when they use different translation functions. An example where this property is useful is running the same program twice in parallel. So we have program 1, program 2, or the same program twice, each of which has access to 0 to 150 in memory, but it's mapped to a different location in physical memory. So they say read from byte 0. This one says read from byte 0, and it reads actually from 100. This says read from byte 0, and it gets translated by the hardware, right, to address 300. So even though they have the same instructions, they refer to different parts of memory. Right, so that's what this is explaining here. First instance is that segment off at 100. So its 0 to 150 are translated to 100 to 250. And the second has offset 300, so that it goes, its 0 to 150 translates to 300 to 450. Another advantage is that programs can be placed at arbitrary physical memory locations now, even if they use completely different virtual addresses. Fragmentation. The differentiation between virtual and physical addresses makes segmentation really powerful. However, it has a problem of fragmentation. As an example, imagine that we want to run the third copy of the program we saw above. We can't map, there's no range, what they're saying here is there's no range that's 150 big. So how do you map this region into here? There's no way to map the third instance of the program to virtual memory without overlapping, even though there is more than enough free memory available. Yeah, so if you add this plus this plus this, there's more than 150, right? There's 100 plus 50 plus another 100 here. So there's 250 bytes free, but there's no contiguous 150 region free. One way to combat this fragmentation is to pause execution, move the used parts of the memory closer together, update the translation, and then resume execution. Right, so now we pause execution, we remap the two running programs to the new locations. We copy the data, right? You have to copy it from physical memory. And then when these programs resume, they don't know anything changed. They still read 0 to 150, and they're mapped just to a different location. And as far as they're concerned, nothing changed. And now we have a region that's 250 large, and we can map the 150 into it. The disadvantage of this defragmentation process is that it needs to copy large amounts of memory, which decreases performance. It also needs to be done regularly before the memory becomes too fragmented. This makes performance unpredictable, since programs are paused at random times and might become unresponsive. Yeah, it's the same thing with garbage collection, right? This is essentially garbage collection for physical memory. The fragmentation problem is one of the reasons that segmentation is no longer used by most systems. In fact, segmentation is not even supported in 64-bit mode on x86 anymore. Instead, paging is used, which completely avoids the fragmentation problem. All right, so paging is the idea to divide both the virtual and physical memory space into small fixed-size blocks. The blocks of the virtual memory space are called pages, and the blocks of the physical address space are called frames. So we have 3 pages here mapped to 3 frames here. Each page can be individually mapped to a frame, which makes it possible to split larger memory regions across non-continuous physical frames. The advantage of this becomes visible if we recap the example of the fragmented space, but use paging instead of segmentation this time. Right, so now this page can map to this frame, and these 2 pages can map to these 2 frames, and we don't have to move these guys anywhere. In this example, we have a page size of 50 bytes, which means that each of our memory regions is split across 3 pages. Each page is mapped to a frame individually, so a contiguous virtual memory region can be mapped to a non-contiguous. Sorry, I'm saying contiguous. You're saying continuous. A continuous virtual memory region can be mapped to a non-contiguous physical frames. That's hard to say. This allows us to start the third instance of the program without performing any defragmentation beforehand. Okay, oops, too far. Hidden fragmentation. Compared to segmentation, paging uses lots of small fixed-size memory regions instead of a few large variable-sized regions. Epic Blog says, I think they mean contiguous. Yeah, I think so too. I think that's why I was reading it as contiguous. And then it just flipped in my brain when I actually read the word they wrote. Since every frame has the same size, there are no frames that are too small to be used, so no fragmentation occurs. Or it seems like no fragmentation occurs. There is still some hidden kinds of fragmentation, the so-called internal fragmentation. Internal fragmentation occurs because not every memory region is an exact multiple of the page size. Imagine a program of size 101 in the above example. It would still need 3 pages of size 50, so it would occupy 49 bytes more than needed. Well, to differentiate the 2 types of fragmentations, the kind of fragmentation that happens when using segmentation is called external fragmentation. Internal fragmentation is unfortunate, but often better than external fragmentation that occurs with segmentation. I'm saying tation too many times now. It still wastes memory but does not require defragmentation, there we go again, and makes the amount of fragmentation predictable on average half a page per memory region, right? Yeah, that makes sense. And in fact, I think pages are what, 4K? So in multi-gigabyte systems, I don't think it's half a page of memory per region. They didn't define what a region was, but maybe it's just a contiguous mapping. Maybe. Because I don't think we lose half of memory when we're normally running. Like if we have a 64 gig system, do we lose 8 gig of that to fragmentation? I don't think that's happening. I think most of the time you fill the frames, right? And there's just the tail end of the frame the tail end of the last part of the frame might be missing half of its, because you're not using up to half. On average half. So I don't think you're losing half of physical memory to fragmentation. All right, page tables. We saw that each of the potentially millions of pages is individually mapped to a frame. This mapping information needs to be stored somewhere. Segmentation uses an individual segment selector register for each active memory region, which is not possible for paging since there are way more pages than registers. Instead, paging uses a table structure called a page table to store the mapping information. So we have to give up some RAM to map the page table in memory somewhere. For example, the page table, for our above examples, the page tables would look like this. Okay, so they're saying this is page 0, maps to frame starting at 100. And I guess we now have memory protection flags, right? We see that each program instance has its own page table. A pointer to the currently active table is stored in a special CPU register. On x86, the register is called CR3. It's the job of the operating system to load this register with the pointer to the correct page table before running each program instance. All right, so every time you start a new program or you switch to a new program, right? We haven't talked about processes yet, and from what I saw from the blog post, I don't think we're going to get to processes. But when the operating system decides a process X needs to start, it needs to retrieve whatever the value is for CR3 for that process. At least on the x86, other chips have different registers, right? But on x86, it has to set the CR3 register first and then start or resume execution of a program that may have been blocked or paused or whatever. On each memory access, the CPU reads the table pointer from the register and looks up the mapped frame for the accessed page in the table. This is entirely done in hardware and completely transparent to the running program. To speed up the translation process, many CPU architectures have a special cache that remembers the results of the last translations. Okay, that makes sense. That way it doesn't have to hit main memory for every memory access, right? It could just look it up in its wherever it stores the page table in its cache. Depending on the architecture, page table entries can also store attributes such as access permissions in a flags field. In the above example, the read-write flag makes the page both readable and writable. Multi-level page tables. The simple page tables we just saw have a problem in larger address spaces. They waste memory. For example, imagine a program that uses 4 virtual pages: 0, 1 million, 1,050,000, and 1,000,100. We use underscore as a thousand separator. And then here we're using space as a thousand separator. Okay. It only needs 4 physical frames, but the page table has over 1 million entries. Oh, right. It has to have entries for each physical page or virtual page that maps to a nothing frame. We can't omit the empty entries because then the CPU would no longer be able to jump directly to the correct entry in the translation process. Right? It has to be able to say, okay, I have memory address 1 million. It shouldn't have to walk the table to find where 1 million is. It's got to be able to jump directly there. Otherwise, you have O of n instead of O of 1. I think that's what they're trying to talk about. Sudo Maze, thank you for the follow. To reduce the wasted memory, we can use a two-level page table. The idea is that we use different page tables for different address regions. An additional table called Level 2 page table contains the mapping between address regions and Level 1 page tables. Okay. So we still need the entries here, but I guess we don't have to store them anymore. This is best explained by an example. Let's define that each Level 1 page table is responsible for a region size of 10,000. Then the following tables would exist for the above example mapping. We'd still have the virtual memory table, right? But it would map this region into a Level 2 page table called T2, and this region would map to a Level 2 page table called, oh no, this is Level 2 page table, Level 1 page table. Okay, so we map from virtual memory to Level 2, Level 2 maps to another Level 1, and then that Level 1 maps to physical. So now we have two indirect levels. I mean, that's a general solution, right? To any issues that you have in computer science, right? If you're writing a program and you have problems, the easiest solution to your problem is to add a layer of indirection. So that's what they're doing here, is adding a layer of indirection. But of course, now any read from virtual memory has to go through two layers of page tables before it hits physical memory. And that's another reason for having the cache, because the cache can remember the direct physical memory access instead of having to go through the two layers of page tables. Page 0 falls into the first 10,000 byte region, so it uses the first entry of the Level 2 page table. This entry points to Level 1 page table T1, which specifies that page 0 points to frame 0. Pages 1,000,000, 1,050,000, 1,000,000, and 100 all fall into the 100th 10,000 byte region. So all of these map to here. So they use the 100th entry of the Level 2 page table. This entry points at a different Level 1 page table. This one points to T2, which maps the three pages to frames 100, 150, and 200. Boom, boom, and boom. Note that the page address in Level 1 tables does not include a region offset. So, for example, the entry for page 1,050,000 is just 50. Right? Yeah, there's no reason to include that part of it because you know that part of it already. We still have 100 empty entries in the Level 2 page table, but much fewer than 1,000,000 empty entries before. The reason for the saving is that we don't need to create Level 1 page tables for the unmapped regions between 10,000 and 1,000,000, right? So when we read the address, this is not a map. This is just an address space. And when we say, okay, read from 1,000,000, we just, in this example, we just divide by the appropriate value to see what the index is. And then we read the location of the page table from that. The principle of two-level page tables can be extended to 3, 4, or more levels, right? Then the page table register points at the highest level table, which points to the next lower level table, which points to the next lower level table, and so on. The Level 1 page table then points at the mapped frame. The principle in general is called multi-level or hierarchical page table. Now that we know how paging in multi-level page tables works, we can look at how paging is implemented in the x86-64 architecture. We assume in the following that the CPU runs in 64-bit mode. So on the x86-64, that's interesting. What are we doing with this region then? So I'm assuming this is an address, right? So x86-64 uses a 4-level page table and a page size of 4K, right? Each page table, independent of the level, has a fixed size of 512 entries. Each entry has a size of 8 bytes. So each table is 512 times 8 bytes, or 4 kilobytes. Thus, it fits exactly into one page. That's convenient. The page table index for level is derived directly from the virtual address. I'm missing, I think this sentence is missing a word, maybe? But I understand what the meaning is here. So we have the page offset, which is 12 bits, right? That would index into a 4K value. At 12 bits represents 4K. And then we have do we have these 4? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have these 9-bit regions that are the index to the 512 page table. We see that each table index consists of 9 bits, which makes sense because each table has 2 to the 9th, or 512 entries. The lowest 12 bits are the offset into the 4K region, right? Bits 48 to 64 are discarded, which means x86 64 is not really 64-bit, since it only supports 48-bit addresses for virtual addresses. I wonder if it can still access these for physical addresses. If a physical address read can still use all 64 bits. Let's see if they tell us. Even though bits 48 to 64 are discarded, they can't be set to arbitrary values. Instead, all bits in this range have to be copies of bit 47 in order to keep addresses unique and allow future extensions like a 5-level page table. Oh, yeah, 5 level. So you'd be able to fit another 9 bits in here, and then you'd have like a few bits left over. This is called sign extension because it's very similar to the sign extension in 2's complement. When an address is not correctly sign extended, the CPU throws an exception. It's worth noting that the recent Ice Lake Intel CPUs optionally supported 5-level page tables. Right, extended from 48 to 57. So we just learned that. Increasing the addressable virtual memory from 256 terabytes to 128 petabytes. Was that all? Epic Blog says, 48 bits only? I paid for 64-bit. I want my additional bits worth of money back. Yeah, I mean, 256 terabytes should be enough for anyone. I'll make that statement, right? Is that a good statement to make? Yeah, if you have, that's what I'm saying about physical versus virtual. This is a virtual address. So any given program in this instance can address up to, why did that scroll? Oh, it didn't. Can address up to 256 terabytes of memory. And with the 5-level paging, you get up to 128 petabytes worth of memory per process. Epic Blog says, everyone knows that the value of the computer is the bits of the address bus. All right. That's, if I can figure out how to do this again, there we go. Everyone knows that the value of the computer is in the bits of the address bus. That's a statement for the ages. All right. I mean, it sort of kind of is, right? Because you're you know, if you're advertising it as a 64-bit processor, although in practice, who's going to use 128 petabytes? And that's 128 petabytes is only 57 bits, so I think we're safe. I don't know. I'm not, I mean, despite the fact that I've been doing kernel programming for, I don't know, a decade or so, this is all, virtual memory is all, was a black box to me until this. So it's interesting to learn that a 64-bit processor only uses less. And actually these segments of the address are not pointing to any physical space, right? This is the only thing that's indexing a memory block, and everything else is just pointing to a page table. That's fascinating. Right. So we read that already. Given that optimizing our kernel for a specific CPU does not make sense at this stage, we will only work with standard 4-level page tables in this post. But we are kind of optimizing for a specific CPU, right? We're only using x86 64. This code wouldn't work on ARM, right? The code we're developing won't work on ARM, for example, or on Spark, or whatever else is out there. 6502. Let's go through an example to understand how the translation process works. Supercuber, hello. Thanks for joining. I'm just reading this over. So the CR3 register, which we learned about above, points to a specific page in memory which contains the level 4 page table for a given process. Every process has its own level 4 page table. What would be neat, though, is if the page table had some sort of indication that says we don't need to go through all the other tables, we can just point directly to a frame. Right? Because if we're only using a little bit of memory, there's no reason to have one entry here, one entry here, one entry here, and then a few entries here. It'd be nice to be able to figure out how to map it directly, but I don't know if there's a way to do that. Let's see. The physical address of the currently active level 4 page table, which is the root of the 4-level page table, is stored in the CR3 register. Right. Each page table entry then points to a physical frame of the next level table. The entry of the level 1 table then points to the mapped frame. Note that all addresses in the page tables are physical instead of virtual, because otherwise the CPU would need to translate those addresses too, which could cause a never-ending recursion. Right, so this is pointing, this level 4 page table says, okay, for index 1, we're pointing to here, and this is physical address here. This physical offset of 16K. And that contains a 4K region of a level 3 page table, which points to this, which contains a level 2 page table, which points to here, right? And which contains a level 1 page table, which points to our actual data. Or actually 2 blocks of data, right? This blue and this blue region. The above page table hierarchy maps 2 pages in blue from the page table indices that we can deduce that the virtual addresses of these 2 pages are hex 803FE7F000 and hex 803FE00000. Let's see what happens when the program tries to read from the address F5CE. First, we convert the address to binary and determine the page table indices and the page offset for the addresses. So the offset is 5CE, these lower 12 bits, right? Then we have, and unfortunately it's not easy to see in this format, right? But it is easy to see in this format. Because these formats are 4 bits and 4 bits, and we need 9, 9, 9, and 9. But we can see we have index 127, 511, index 0, and index 1. And then the sign extension, this number has to match this number here. So we can now walk the page table hierarchy. We start by reading the address of the level 4 table out of the CR3 register. Level 4 index is 1. So we look at index 1. It says level 3 is stored at address 16K, or 16384, right? And then we load that table from that address and look at the entry with index 0, which says we're at 24576. Level 2 is at index 511. So we look at the last entry of that page to find out the address level 1 table. Through the entry with index 127 of the level 1 table, we finally find out that the page is mapped to frame 12K, or 3000 hex. The final step is to add the page table to the frame address to get the physical address. Right, so we're adding this offset to the start of the frame, and we get the physical address of the 35CE. The permissions for the page in level 1 are read, which means read only. The hardware enforces these permissions and would throw an exception if we tried to write to that page. Permission in higher level pages restrict the possible permissions on lower levels. So if we set the level 3 entry to read only, no pages that use this entry can be writable, even if lower levels specify read-write permissions. It's important to note that even though this example used only a single instance of each table, there are typically multiple instances of each level in each address space. At a maximum, there are 1 level 4 table, 512 level 3 tables, 512 times 512 level 2 tables, and 512 cubed level 1 tables. Page tables on the x86-64 architecture are basically an array of 512 entries. In Rust syntax, it looks like this. A line on a 4096 boundary. We have a page table entry 512, and we don't know how big those are. Actually, we should, right? We should know how big those are. Epic Blog has another quotable statement here. It takes a while for this thing to come up, doesn't it? It occurs to me why page table caches are so important for performance. Yeah, because all these extra reads, every time you're doing a read, right, you end up having to go through all of these page tables. So the first time you hit a particular page, it's slow, right? And so caching this in the CPU for future reads is good. And you want locality of data. If you're reading data, you don't want to have data here and then, if you're reading sequential data, you don't want them in separate pages. You want them all contiguous. And that's one of the reasons that ECS is a big boost to performance for games, is that you putting similar data in contiguous memory, so that as you're processing it, you can do sequential memory accesses, and the CPU can prefetch the pages based on your read pattern and your write pattern. All right. As indicated by the repr attribute, page tables need to be page aligned, 4K. This requirement guarantees that a page table always fills a complete page and allows an optimization that makes entries very compact. Each entry is 8 bytes. Right. So we have 512 entries of 8 bytes each. And this is the layout. I'm not going to read the whole table out. But the bit 0 is the present page, says whether or not it's in memory. This is for paging systems, right? So you can page out a piece of, or you can page a frame to disk, or write out a frame to disk and reuse it for something else. And then the next time somebody goes to read from that page, it'll see that this bit says that it's not present in memory and you have to go fetch it. Creator of Iniquity says 500 followers on Twitch. Did I get to 500? Oh, I'm at 501. So I guess it was Sudumaze was 501. Somebody named Plop23 followed me 16 hours ago when I wasn't streaming. It was my 500th follower. Thank you for pointing that out, Creator of Iniquity. I wasn't even paying attention. Very cool. 501 followers. Got to get to 512, right, for page table entry. And Fernando reads with a party of 47. Thank you, Fernando, for that for the second raid. Yeah, I was looking. I looked at your channel briefly. I don't understand Portuguese, so obrigado. I can say that. Curve KGB 6X, thank you for the follow, and Celisbrack 1, thank you for the follow. The other phrase I know is Bishu de Lishu, and that was something I learned a long time ago, but I don't know any Portuguese beyond that, I'm afraid. Okay, so we looked at this briefly. I don't want to read every single thing in the table. I do want to get to some code today. Let's see. We see that only bits 12 through 51 are used to store the physical frame address. The remaining bits are used as flags or can be freely used by the operating system. So we have 64 bits per entry, and we only use 0 through 11. 12 through 51 says the page line 52-bit physical address of the frame or the next page table. Okay. Then we have 10 bits that are available for the OS, and then we have the no execute bit. I'm doing very well, Fernando. Thank you for asking. I'm excited to get back into this operating system stuff. There aren't too many more left for this, so I have to think of what comes next after this, and maybe I'll get back into my roguelike. How was your stream? Hopefully it went well today. Right. The remaining bits are used as flags or can be freely used by the operating system. This is possible because we always point to a 4K aligned address, either to a page-aligned page table or to the start of a mapped frame. That means that bits 0 through 11 are always 0. Oh, good. I'm glad your stream went well. It's always fun when you have a good stream and good interaction. Bits 0 through 11 are always 0, so there's no reason to store those bits because the hardware can just set them to 0 before using the address. The same is true for 52 to 63, because the x86-64 architecture only supports 52-bit physical addresses. Oh, okay, so this is new, right? So it supports 48-bit virtual addresses and only 52-bit physical addresses. And yet it's still called a 64-bit, right? Because that's what this x86-64 stands for, right? Although the data registers use all 64 bits, right? So you still have 64 bits for that, just not for addressing. Let's take a look at the available flags. So it means that you have a bunch of bits at the top of the physical address that you can use to store tiny bits of information in. And we actually saw that in the crafting interpreters code. I don't think I have that here. In crafting interpreters, they actually, in the C version of the interpreter, they stole a few of the upper bits for data. Let's take a closer look at the available flags. The present flag differentiates mapped pages from unmapped ones. It can be used to temporarily swap out pages to disk when main memory becomes full. When the page is accessed subsequently, a special exception is called a page fault occurs, to which the operating system can react by reloading the missing page from disk and then continuing the program. The writable and no execute flags control whether the contents of the page are writable or contain executable instructions, respectively. The accessed and dirty flags are automatically set by the CPU when a read or write to the page occurs. This information can be leveraged by the operating system, for example, to decide which pages to swap out or whether page contents were modified since the last save to disk. Right. If you're trying to claim a page and the dirty flag is not set, that means you don't need to write that page out to disk because the page in memory and the page on disk are identical already. If the dirty flag is set, that means this does need to be written out to disk before it can be used for something else. Access can be used to determine whether or not a page is being actively used, which means maybe if you're trying to find memory to swap out, you favor pages that haven't been accessed since the last time you looked, because those are less likely to have to be paged back in again. The write-through caching and disabled cache flags allow to control the caches for every page individually. I'm trying to remember. Write-through caching probably means that if you write to this page, it also writes to the a backing cache somewhere, which makes things a little slower, but a little more resilient, I guess. Disable cache. I'm trying to think of reasons to disable a cache on a memory. It could be like if it's a temporary scratch space, but you still need to be able to. Yeah, I don't know. I'm sure there's legit reasons for it, otherwise it wouldn't exist. But I can't think of any off the top of my head. The user accessible flag makes a page available to user space code. Otherwise, it is only accessible when the CPU is in kernel mode. This feature can be used to make system calls faster by keeping the kernel mapped while a user space program is running. However, the Spectre vulnerability can allow user space programs to read these pages nonetheless. Yeah, I don't want to dig into that, but that was basically using cache or memory read speeds to determine whether or not a page was cached and then be able to learn information about it. The global flag signals to the hardware that a page is available in all address spaces and thus does not need to be removed from the translation cache on address space switches. This flag is commonly used together with a cleared user accessible flag to map the kernel code to all address spaces. The huge page flag allows to create pages of larger sizes by letting the entries of the level 2 or level 3 page tables directly point to a mapped frame. Ah, yes. That's what I was asking about above. You could reduce the number of indirections by having level 2 or level 3 point directly to a frame. With this bit set, the page size increases by a factor of 512. The advantage of using larger pages is that fewer lines of the translation cache and fewer page tables are needed, and fewer levels of indirection are needed when you're reading from memory, right? The x86-64 crate provides types for page tables and their entries, so we don't need to create these structures ourselves. The translation look-aside buffer. A 4-level page table makes the translation of virtual addresses expensive because each translation requires 4 memory accesses. To improve performance, the x86-64 architecture caches the last few translations in a so-called translation look-aside buffer. This allows to skip the translation when the translation is still cached. I don't know if this is like regional phrasing. In my region of English, I would insert the word "it" in here. This allows it, meaning the CPU, to skip the translation when the translation is still cached. Maybe there's some regions of English that omit the preposition there. I don't know. It's new to me. Unlike the other CPU caches, the TLB is not fully transparent and does not update or remove translations when the contents of the page tables change. This means that the kernel must manually update the TLB whenever it modifies a page table. To do this, there is a special CPU instruction called invlpg, invalidate page, invlpg, okay, that removes the translation for the specified page from the TLB so that it is loaded again from the page table on next access. The TLB can also be flushed completely by reloading the CR3 register, which simulates an address space switch. The x86-64 crate provides Rust functions for both variants in the TLB module. It's important to remember that flushing the TLB on each page table modification, because otherwise the CPU might keep using the old translation, which can lead to non-deterministic bugs that are very hard to debug. Implementation. One thing that we did not mention yet, our kernel already runs on paging. The bootloader that we added in the minimal Rust kernel post already sets up a 4-level paging hierarchy that maps every page of our kernel to a physical frame. The bootloader does this because paging is mandatory in 64-bit mode on x86-64. This means that every memory address we used in our kernel was a virtual address. Accessing the VGA buffer at address B8000 only worked because the bootloader identity mapped that memory page, which means that it mapped the virtual page B8000 to the physical frame B8000. Paging makes our kernel already relatively safe, since every memory access that is out of bounds causes a page fault exception instead of writing to random physical memory. The bootloader even set the correct access permissions for each page, which means that the only pages containing code are executable and only data pages are writable. Okay, so now we're going to get to some code. Let's try to cause, oops, I got to move this over a little bit here. Let's try to cause a page fault by accessing some memory outside of our kernel. First, we create a page fault handler and register it in our IDT so that we see a page fault exception instead of a generic double fault. Okay, so now we get to write some code. This is what I live for. So in our interrupts module, we have this table over here. We have these here. This is a set. Okay, so we're going to just add a new IDT page fault set handler function. Page fault handler. Okay. And we have this page fault error code in IDT now. And then we already have our halt loop somewhere, right? No. Okay, so that's something we're adding here for our page fault handler. All right. And now we're going to add a new interrupt function here, extern x86 interrupt. We have an interrupt stack frame, and this is the first one that has an error code in it. Right? Right, this one had a stack frame. So this is the breakpoint handler, which just had a stack frame. This is a double fault handler, which had a stack frame. It did have an error code here that we threw away. Because as I recall, it's always set to 0. Here's a timer interrupt handler, which does not have a error code. And then a keyboard interrupt handler, which I demoed just at the beginning of the screen. Okay, so this is the page fault error code. Use x86 64 registers control CR2. Fault. Accessed address. And we're going to just debug this out. Of CR2 read. And then we have an error code of whatever it's going to turn out to be. We can do it this way now. This blog must have been written before we had this feature in Rust. And then we can print line the stack frame as well. Stack frame. Like that, and then we hit the halt loop. And so that's our whole page fault handler. The CR2 register automatically set by the CPU on a page fault and contains the accessed virtual address that caused the page fault. We use the CR2 read function of the x86-64 crate to read it and print it. The page fault error code type provides more information about the type of memory access that caused the page fault. For example, whether it was caused by a read or a write operation. For this reason, we print it too. We can't continue execution without resolving the page fault, so we enter a halt loop at the end. Now we can try to access some memory outside our kernel. All right, let's see if this builds. It does not, because I did that. It still does not, because stack frame. Oh, because I called it stack farm. There. Okay. We can try to access some memory outside our kernel. So in main, in our start function, right after we do the init, we're going to try to read let pointer is equal to dead beef as U32. So unsafe, we can try to write to it. Come on. There we go. Okay. So when we run it, we see that our page fault handler is called. Okay, cargo run. Bam. There's the hello world. There's the exception that we print out. Our virtual address is dead beef, caused by a write. This was the instruction pointer. It's slightly different to what they have, but that's fine. CPU flags are a little bit different. And then the stack pointer is somewhere. Wow, that's very different. Okay. Quit. All right, but we see the page fault being called. Page fault handler being called. CR2 register indeed contains dead beef, the address that we tried to access. The error code tells us through the caused by write that the fault occurred while trying to perform a write operation. It tells us even more through the bits that are not set. For example, the fact that protection violation flag is not set means that the page fault occurred because the target page wasn't present. We see that the current instruction pointer is this number, so we know that this address points to a code page. Code pages are mapped read-only by the bootloader, so reading from this address works, but writing causes a page fault. You can try this by changing dead beef pointer to that value. Okay, so let me see what that value was again. it won't change, right? I can't copy paste 205.413. Let's just remember that. 205.413. 205.413. And if we tried to, oh, they have read and write. Okay. Let x equals pointer, and then we can just say println read worked. And then we try to, excuse me, and we write to it, unsafe, and then write worked. Okay? 2 warnings. That's fine. Okay, so now we see read worked, and then we have a failure on write. So we were able to read the, oh, now the instruction pointer is slightly different. But that's okay, because we were able to do the read. By commenting out the last line, we can see that the read access works, but the write access causes a page fault. This must be leftover text somehow. We see that the read worked message is printed, which indicates that the read operation did not cause any errors. However, instead of the write worked message, a page fault occurs. This time, the protection violation flag is set in addition to the caused by write flag, which indicates that the page was present, but the operation was not allowed on it. Oh, I missed that. Oh, there it is. Protection violation caused by write. Neat. Accessing the page tables. Let's try to take a look at page tables that define how our kernel is mapped. Okay, so instead of having that bad code in there, we're going to get rid of this code here. And we're going to say use x86 64. Let level for page table is equal to cr3 read, and in println at this location, level for page table start address. I wonder what other information there is on the level 4 page table. It's a fizz frame. Oh. Interesting. Okay. Let's see what it says. So the level 4 page table is at physical address 1000, hex 1000. Okay. Yeah, it's the same as this one. So the currently active level 4 page table is stored at physical at address 1000 in physical memory, as indicated by the phys_adder wrapper type. The question now is, how can we access this table from our kernel? Accessing physical memory directly is not possible when paging is active, since programs could easily circumvent memory protection and access memory of other programs otherwise. So the only way to access the table is through some virtual page that is mapped to the physical frame at address 1000. This problem of creating mappings for page table frames is a general problem, since the kernel needs to access the page tables regularly, for example when allocating a stack for a new thread. Solutions to this problem are explained in detail in the next post. All right, let's commit these changes. Printing, let's see, page table handler and page fault handler, and displaying level 4 page location. Good. All right, so I think we're good with this one, right?